You guys a little demo, and it was going to be a live demo, but I found the cart and I couldn't find the remote for the cart, so we're going to watch it. Someone else do it. He's very lively though, so don't worry. But it is a good demo.
The vertical and horizontal motions of a projectile do not influence each other. The projectile that we'll use is this plastic ball, and we'll project it with this cannon. This cannon, this device has a spring in it, and I'll just hold it here so you can see it. And I can force the spring down, and it will stay in place there. So the spring is compressed at this point. I'll push the cart along this level track. My table's not quite level, so I put some cardboard here to make sure that it was level. So you can see the cart doesn't move on the track. The other thing that I need is to release the ball, and for that purpose I have an automatic release, which is a photo gate. The photo gate is this device on the side, which has a slot in it. There's an infrared beam passing across it. If I break that infrared beam with something, then that will release the ball. What I'll break it with is this piece of cardboard. So I'm going to mount this cardboard on this clamp right here at exactly the level of the photo gate, and double check. Now when I pass it through, I'll just show you how this works. When I pass it through the photo gate, it releases the ball.
You just catch that? That's amazing.
Cat-like
So I'll get the flag in position, line it up, and we're set to go. Ready the cart. I'll give a push, and I'll stop pushing before the flag actually passes through the photo gate. And as you can see, the ball fell right back down into the cannon. Let's take another look at that. Ready? Right back down in the cannon before I actually caught it over here. So what that is showing us is that the ball continues traveling horizontally with the same speed that the cart has. The cart doesn't slow down, the ball doesn't slow down, and since they're both moving horizontally together, the ball comes right back down in the cart. And the fact that gravity was acting on the ball all the time and making it slow down on the way up and speed up on the way down had absolutely no effect on that horizontal motion.
Okay, so it shows, this idea that's been coming up that Y and X motion is independent in these problems, which makes it easier to solve the problems. And it also, you can see it has some cool things that come out of it. So because he knows that it's going to maintain the same speed in the X direction, right, it will hit that cart, so you can cool things like this demo. So hopefully that's not too surprising. Have you guys seen stuff like this before? Maybe like a demo? Sometimes they talk about like, instead of like launching it from the ground, releasing something out this way, and then having, so launching two things, one along the ground and one that's falling, and you can catch it, that way too, because as long as they have the same speed initially, nothing is going to change in the acceleration of the X for either of those, as long as there's no external forces acting on it. Okay, so we talked about last time the zero launch angle, right? So this is when you launch something horizontally and then it falls down. So the homework problem that you did that, right, where she's running with the keys and she drops the keys. And we did a bunch of examples, where someone is, running or skiing off of a cliff, right, jumping onto over that crevice. Right, do you remember this? Yeah, on the crevice, and we had to say like how fast you have to go to land safely on the other side. But you can also, have angles, beginning angles that are other than just, along the X direction. And so you still take the same approach, right? So you just write down all the variables that you know. When you have a initial velocity that is not along the X, then you have two components of it. So then from those two components, you get V naught X, V naught Y, right? And so your V naught Y won't necessarily be 0 in the general case. But it's the same approach, right? And you just figure out what variables do you have, plug them into your equations, and then those may simplify depending on, what the situation is. Especially, AX is going to be 0. So we're going to jump right into examples, and we're going to just go through examples today. The first one is about a cheerleader that's thrown straight up into the air. So this one is, if you recognize it, not even projectile motion, it's just free fall, right? Because she's going straight up into the air, so we're not even worried about X component yet. But this is just kind of warm up. So the cheerleader is thrown straight up into the air. Assuming that the cheerleader is launched and caught at the same height, what is the initial velocity of the cheerleader if she's airborne for t equals 0.65 seconds? So it might seem like there's not a lot of variables I give you. But I want you to write down as you notice where the variables are. Keep in mind that she's in free fall. I forget what the answer is, but if you found one, I didn't. Okay, so what are we thinking? What variables do you know? Someone give me one. I heard time and delta x. Time is 0.65 seconds. What's delta x? 0. Good. How about another one? Delta y is also 0. Very good. How about another one?
AY is G or
Okay, we'll say down is negative. So we'll do AY is,
so AX is also 0.
AX is 0. AX is getting real boring, right?
VOX is 0.
VOX is 0, wonderful.
VX is 0.
VX is 0. Look at how many variables you have. A lot of them are 0, but look at how many we've already picked up. So now we can go through and we have all of the A's, right? We have all the delta x, delta y's. These displacements. We have time, which is a good one. No. Okay, so time. And then we also have VOX. Look at this one's completely, there's just nothing here, right? Everything here, right? This one, we can solve for VX. Oh, do we already have that? We already have it. We have literally everything here. X just, nothing's happening in the X. So when you solve for any of it, right, nothing's gonna happen. All right, when we look over here, I see this one has 2 unknowns. Yes. This one has 2 unknowns. This one only has 1 unknown. And it's the one that we're looking for, which is V naught y. Right? So you could solve this equation for V naught y. So what will that look like? That'll be delta y is 0, right? So I'm not going to plug anything in besides the zeros, because zeros make it nice and easy. So delta y is 0 equals V naught y t plus 1/2 a1 t squared. And I want to solve for Vy, so we do V naught y t equals minus 1/2 AYT squared. And then we could divide by t on both sides, so divide by t, something like that. So, I asked for the speed. I should have said speed because velocity should be a vector, right? So I changed it on the second slide, but not the first slide. So the initial speed of it. Did you get good? Some agreement? Calculator skills are okay? Excellent. So even when the question seems like, wait, I'm only given time, right? Yes, but that's explicitly your given time. But when you know that the problem is about free fall, or if you can kind of determine that there's no x components of things, that helps a lot. Yes?
Can you like split it up?
Can you split it up? How so?
Mm-hmm.
You could also split it up. So you could think about what happens at t equals a half. At t equals a half, then your Vy would be, if you're thinking about the first leg of the trip, So these would just be different depending on how you do it. But yes, you could split it up too. And that will give you different. Very good. Other questions on this? All right. So now we have a two-dimensional problem. But remember, and it might seem like there's a whole lot of things to keep track of, but just remember the process, right? So draw yourself a picture, identify variables in the question, go on from there, find equations, right? So chipping from the rough, a golfer sends the ball over a 3-meter tree 14 meters away. The ball lands at the same elevation after traveling a horizontal distance of 17.8 meters. If the ball left the club at 54 degrees above the horizontal and landed 2.24 seconds later, what was its initial speed? Right, so this was the opposite of the other one. It's like, oh my gosh, there's so many numbers floating around in here, versus the other one's like, there's like one number, right? Oh my gosh, right? But you can do it. Just break it down into what the variables are. Oh, were you using those? I'm going to rewrite those. So
Okay.
try to write them down from memory, and then you can check to see if it matches mine. So we can recircle it. It's going. It's going okay. All right, so you got some variables written down. Good. And we're thinking about the initial speed, right? So that's the magnitude of the velocity vector, which takes, this component squared plus this component squared square rooted. So these are the ones that we want to find for this problem. Yes. All right, so so wouldn't it be nice if instead of looking for two variables, we could just look for one variable, right? Could we write these variables in terms of the same variable that we don't know?
Yes.
Yes. Okay, Ben, how do you write it?
V of x equals cosine, or, yeah, would be the, yeah.
V naught.
Cosine of 54 degrees.
Very good. And then this one is?
V naught times the sine of 50.
So now we really just have one variable that we're looking for, right? So both Vx and Vy just depend on whatever V0 is. We already know what the angle is. So once, if we just knew V0, we could easily figure out what are the x and y components of it. So now we have one variable here that we're searching for, this V naught, and then we also have these variables that we already know. Okay, so the breaking it down, this step, may be the trickiest, I think, of this question, right? Is identifying that you can relate these two, right? To just V0. So now, if you look at your equation options, we could solve for either V naught x or V naught y, and we would get V0, right? So either one of those will give us the answer that we're looking for. V0 is the speed. So which of the equations could you use with these variables to solve for V0? Should we circle them? Did you circle them on your paper? The delta x or the delta y equation of love. So if you haven't done this step on your own and you're stuck, you should, when you're stuck, write down all these equations, write down all your variables, and then do the little circling thing that we do, right? Because then you can very clearly see which one to use. So if we do that, and we have the hint that it might be the delta x or delta y equation of love, which one? We could pick either one, really. So we have time, we have a, both ax and ay, and we have the delta x or delta y. So we could use, either this one or this one, and solve for either v naught x or v naught y, and plug in, this to get our v naught. Yes. Is it okay? Is it okay that I just said it in words? Do you want me to write it? How is this? Can I get like a thumbs up, medium, thumbs down? It's okay if it's like it's medium. That's fine. It's okay. Do you want me to see me to write it? Okay. All right. Good. So if we take delta x, this delta x equation of love, I'm gonna do the x just because I like x better than y today. So v naught x t plus 1/2 at squared. And this one was picked because we know delta x, we know t, and we know ax. So we could solve for v naught x, right? So if I plug in ax is 0, right? That's the only thing that's 0. So I'm going to plug that in first just to make the expression a lot simpler. So I'll have delta x equals v naught x t. And then I'm going to plug in my other variables that I know. All right, so delta x is 17.8 meters. V naught x is v naught times a cosine of 54 degrees times the time, 2.24 seconds. So now I have a number equals V naught times number. So you could divide both sides by 2.24 seconds times cosine of 54 to get your V naught. And I will write down what we got for V naught, which I got 13.6. Did you get agreement there? Okay, good. So I'll say, just for the next, because we have more questions on this, so I'll write down 13.6 meters per second. All right. Next question is, how high was the ball when passing over the tree? I recommend starting all the way over, right? You can keep the same picture, but rewrite your variables, keeping in mind what is initial and what is final, right? So in this last problem, we took initial and final to be when it left the ground is the initial, and when it hit the ground is the final, right? But now I'm not asking about, that final is different, right? Now I'm asking, how high is the ball when it's passing over the tree? So take your final to be when it's passing over the tree, when you write down what your variables, known variables are. How's it going? If you're maybe stuck, did you get to at least this part? Right, so you have these variables, and they're okay? Anyone disagree with my variables? Variables are okay. Yeah, and you see where I get them all? So the initial condition hasn't changed, right? Our initial is still when it launches. So initial speed is still the same, right? V naught is still the same. VOX, VOY, still the same. Our delta x now, right, is just that 14 meters. Delta y is what we're looking for. AX, AY, it's in free fall, it's in projectile motion, right? So we know those. And then hopefully you wrote these down for yourself. And maybe even from memory, you can write down what the three are. I highly recommend committing these to memory. And then circling what we have. So do you see an equation up here where there's only one unknown variable? The delta x equation of love. So this one has one unknown variable. This one has two. This one has one, right? So this one, the unknown is Vx and t. This is t. This one's Vx. This one has two, Vy and t. This one has delta y and t. This one has Vy delta y. So this is the only one with one variable that's unknown. And it's not delta y, it's t. But if we solve for t, then we'll have another variable that we could circle on our equations, right? So we could use the delta x equation of love to solve for t. If we do that, this is nice because it's 0. So I always plug in 0 first. And then if we are just looking for t, it's going to be delta x over v naught. What do you get for t?
One.
1.76 seconds. Okay, good. So now we have t. So we can circle t. And so this is not going to give us anything more, right? And so we want to look now for another equation that has one unknown. And so we have this one has one unknown. This one is completely solved, so it's useless now. This one has one unknown. This one has one unknown. This one has one unknown. This one has two. And now we want to see what are, okay, so we're looking for delta y. Are any of these one unknowns delta y? Yes. The delta y equation of love. So now you can plug in your v naught y, t, a, y, and t to get what is delta y. This one okay? So we've seen a couple of examples where you read the question and you're like, what the heck? Yeah, good question.
15 meters.
15 meters. It's much bigger. Okay, so, okay, let's go through. Did you get the same time?
Yeah.
Good. When you plugged in, let's see, for your delta y equation of love, what did you put in for v naught y?
13.6.
Ah, so you did what Dom did, but just in the second step. So 13.6 is v naught, but we want v naught y in the y flavor. So be careful, whenever you're in your equations, make sure you're using the component that goes with that flavor of the problem. Good, yes.
I used the 754 and it still got existing. I don't know if it just didn't have
So if you take sine of 45 degrees and cosine of 45 degrees, you'll get exactly the same answer. So 54 is not that far from 45, so it could just be within rounding error. I may be wrong, but be careful when it's angles that are farther from 45 degrees. You will get different answers. So it just happens to be a lucky coincidence, I think. Although I would have to double check your work to be exactly sure, but that's my suspicion, is that cosine and sine of,
Like 15 and 16, so it's not really close to the 4.2.
oh, it's not?
No.
Okay.
That's why, it's like.
What mode is your calculator in? Is it in radian?
I changed it out, like, I don't know if it's in degrees.
It's in degrees, okay. And so you plugged, okay, so did you get the time the same?
Yep, I have one.
Okay, and then when you plugged in here, you plugged in V naught sine of 54
Yeah.
times your time?
The 1.76 and then the 1/2, and then I did it once with -9.8 and then t
Uh-huh.
squared. So it's 1.76.
Okay, I'll have to take a look at it, because I'm not sure. It sounds like you're going on the right path, though. So it's probably just something translating to a calculator. Which calculator errors, they happen, but we can look at that later. All right, but the big takeaway is, so no matter whether you feel like you have way too much information or not enough information, just try to get started. Draw yourself a picture, write down your variables, write down equations that could be useful, and then try to do that little circle thing to figure out which equations could help you out. All right, so the next example, we have a projectile that's launched from the ground with a speed of v naught and an angle of theta with respect to the horizontal. And I want to know, what is the range of the projectile? So the range is how far along the x-axis does this thing travel? And I'm calling it r. So again, even though I'm not giving you numbers, write down the variables. And these, things might just be numbers. Let's do this one together since we're getting close to time. So, what variables do you know?
AX is 0. Well,
X is 0.
is it saying it's just launch without any,
Yep, it's projectile motion.
okay.
So yes, X is 0, AY,
-8,
negative. Oh, yeah, let's just do G.
Yeah.
All right, so we'll call minus G. All right, so delta Y, 0. Delta, T, do we know T?
No,
No, so we don't know. Do we know V naught X?
no. We should probably write in the cosine theta.
Uh-huh, so we do know it, since we know VO and we know theta, we technically know it.
Sort of.
Sort of, I guess you kind of have to draw it. All right,
Theta.
yes, sine of theta. All right, and then we want to know what is the range, which is this. So this is what we're looking for. We're trying to get, something, an expression for R. All right, so we know delta Y and the A's. So delta Y, A. And then we know the V naughts. And we would really like a delta x. So let's see, is there something where, okay, so we have a t here that's unknown, that's an unknown. And if we had t, then we could get delta x,
Right.
right? So that could be one way to do it. Another way that you could think about it is, Caitlin mentioned this before, right? So we could break it into, well, way back in like the first example, right? So when you said, can we break this down into 2 pieces,
Yes.
right? So that could be another way. So these could be your variables, or, you know, if you think about your initial being, you know, when you launch it and your final being at the peak of it, right? So then our delta x would be r over 2. Delta y, we wouldn't quite know. Ax and ay would still be the same, so ax 0, ay minus g. T, we wouldn't know. V naught x and V naught y would still be the same. It'd be V naught cosine theta, V naught sine theta. Right, so then you could circle different variables. I forget which one I went here to get the expression, the final expression for it. I think I probably used the halfway one, is my gut instinct, but I would have to do both of them to check. So let's see. So if I use, I think it's this one that I used to get that answer. So if I had delta x, or maybe not, maybe I used,
No, you probably did because you would multiply by 2 with delta x sine.
Yeah.
Sine 2.
mhm. But I think you still need to, let's see, oh, because then I would know my v x, x, v, o, y. So this is going to be v naught, or sorry, vx. This is going to be the same as v naught x, right, because acceleration is 0. This is going to be 0 then.
Yes.
Yes.
Because that's peak.
Because it's at the peak. So at half of the range, the final velocity in the y direction is 0. Which is, I think, why I chose this one. So that I could do, that I didn't have to work with the quadratic stuff. So let me see, if I do, wow, I guess I could rewrite them all. But we were a little bit, well, we got a minute, I can do it. All right, so let's see. What equation stands out? If I have Vy final is 0, and I have V initial, I have Ay, it looks like this one can give me delta y. That won't help. I really want a t. I want a nice t. This one maybe, yes. So let's see. If I have Vy final is 0, V naught y is this V naught sine of theta. I have Ay is minus g, and then t. So I can solve for t, and I get gt equals V naught sine of theta. So t is equal to V naught sine of theta divided by g. And then, now that I have my t, I could plug that into, I think, the delta x equation of love. So delta x, you know, what we're looking for. And remember that this is going to be r over 2 because we're at, you know, the initial and final is from 0 to, you know, r over 2. Is equal to v naught x t plus 1/2 ax t squared. Ax is 0, which is good. So we have r over 2 equals v naught x times t, and that t is v naught sine of theta over g. This v naught x is really v naught cosine of theta. So I must not have solved it. Oh yes, yes. Sine. So when you have 2 sine times cosine, that's cosine of, sorry, that's sine of 2 theta. Little trig identity. Weird trig identities, right? So this one's a little tricky in that 2 cosine of theta sine theta is equal to sine of 2 theta.
We have to memorize that for the test.
I will probably stray away from that. So no, I wouldn't say that you would need to show your trig identity on it. But on a homework, I might have that. Because you would have more time to think about it. Right? Trig identities. Always a good way to end a Friday, right? Have a good weekend. And there are more examples. Keep in mind there's those quick questions that I have at the end. But be sure to take a look at them because like I said, I will be taking, at least one of them either directly or with a tiny modification for the test. Yes. Okay. Did you get the time? No, it was different.
She just forgets. And it's in Greece. I'm not sure why people do answers.
So let's see, you have 13.6 and the cosine of 45.
Is it goes with the form of problem?
Oh, it's 53.